Hello, welcome to this first interactive lesson. I am Mr. Mason. I'm going to start with a little overview of what we've got going today. So this lesson is designed for Year 7 and it's the higher set. So that's sets X1, X2, Y1 and Y2. Now, if you're not one of those sets, you are more than welcome to continue to watch. But some of the content might be a little tricky and it might be things that you haven't yet seen before. Okay, so just bear that in mind. What I'm going to be doing today is I'll start by going over the solutions from the 5 a day. So that was in the first 5 minutes of the lesson. So you can go back and watch that again if you need to. But I'll go over the solutions and then I'm going to introduce today's topic. And you will probably need some pen and paper today to do the work that we're going to do. So if you haven't got any pen and paper, go out and find some now. So to start with, we're going to look at the solutions to the 5 a day questions. So this was the first one here. We've got Harry earns £9 per hour and works 7 hours. Carly earns £11 per hour and works for 6 hours. And we want to find out who earns more money. So to work this out, we've got a couple of things we need to calculate. We need to calculate how much Harry earns and how much Carly earns. And Harry is going to earn £9 per hour, and he's going to do that for 7 hours. So that's 9 times 7, and 9 times 7, of course, is 63. Carly is going to work at £11 per hour, and she's going to do this for 6 hours, and 11 times 6 is 66. So who earns more money? Well, Carly earns more money, and she earns £6 more. Question 2, we have Kelly needs 5.13 metres of ribbon and she has 1.7 metres. How much more does she need? Well, this is going to be a simple calculation here. We're going to have 5.13 and she's already got 1.7 and we need to work out the difference between 1.7 and 5.13. So all we need to do is do 5.13 subtract 1.7. That will be the difference. So I'm going to start here by carrying the 3 over. I'm going to borrow 1 from there and move it over here. So 11 subtract 7 is going to be 4. And then we've got 4 minus 1, which is 3. So 3.43 metres is how much more she needs. Next, we're going to work out 918 plus 495. So 918, 495. I'm going to use the column method. So 8 plus 5 is going to be 13. We do the 3, carry the 1. 9 plus 1 plus 1 is going to be 11. We carry the 1. 9 plus 4 plus 1 is going to be 14. So 1413. 1413 is our answer. Next question is going to be 27 multiplied by 254. So 27 multiplied by 254. Now there's a few strategies you could take here, but I am going to do a sort of grid method. So I'm going to write down 20 and 7 here. I'm going to write down 250 and 4 here. So we've got 254 multiplied by 27. And now I just need to multiply each of the parts together. So 20 multiplied by 200 is going to be 4,000. 20 multiplied by 50 is going to be 1,000. 20 multiplied by 4 is going to be 80. 7 multiplied by 200 is 1,400. 7 multiplied by 50 is 350. And 7 multiplied by 4 is 28. And now we need to add together all of these parts. So we've got 28, 80, 350, 1,000. Oh, let's undo that and make sure that it's labelled properly. 1,000, 1,400, and 4,000. So we just need to add up all these numbers together. So we've got an 8 in the units column. We've got 8 plus 2 plus 5, which is 15. So that's 5 with 1 carried over. We've got 4 plus 3 plus 1, which is 8. And then we've got 4 plus 1 plus 1, which is 6. So 6858, 6,858 is our final answer. And then the last question, we've got Georgina has made a mistake. So she's tried to add up she's tried to subtract 149 from 698, and she seems to have made a mistake, and we need to figure out what that mistake is. So I think a good way to do this is to actually do the subtraction. So we've got 698, and we're going to subtract 149. So first of all, in order to subtract 9 from 8, we're going to have to just take 1 from here. So we've got 9 subtract 18, that's going to be 9. We then have 8 subtract 4, which is 4, and we've got 6 subtract 1, which is 5. It looks like here, this is the mistake compared to here. So can we explain the mistake? Well, I guess what she should have done is she should have borrowed 1 from this 9, reduced it to an 8, and then made this an 18. And then here we can see 18 subtract 9 is not 1, but it is in fact 9. Now what we're going to go on to today is we're going to be looking at algebra, and specifically we're going to be looking at sequences with algebra. Now I'm going to start by introducing a man called Leonardo da Pisano. Okay? This is a famous mathematician. You may not have heard of him by this name, but you will have heard of him by his more famous name, which is Fibonacci. And that is who we're going to be looking at today. Now, Fibonacci lived around 1200 AD, so quite a long time ago, 800 years ago, in fact. He was born in 1170, and he died around 1250. This man studied a lot during his time. In particular, he looked at something called the Fibonacci numbers. Now, you may have heard of the Fibonacci sequence before, and you may have seen it before in one of your lessons, but if you haven't, don't worry, we're going to have a look at it now. Now, this sequence of numbers appears a lot in the natural world. For example, you could see it in the arrangement of leaves on stems, or maybe petals on flowers, or in this case, we've got the pattern of bee reproduction. So when bees give birth and they have either male or female, this is a pattern that occurs in the reproduction of bees, and it's all over the natural world. Now, what I want you to do to start with is I want you to have a look at the sequence. I'm not going to give away what the rule is in order to generate this sequence, but I want you to try and think of what would the next 7 numbers be in this sequence. Pause the video now, give yourself 5 minutes to work that out, see if you can figure out what the pattern is, thinking, how do we get to the next number? And then see if you can generate the next 7 terms in this sequence. I'm going to give you 5 minutes for that. Pause it now. So hopefully you've had a think about that now and you've tried to come up with the next 7 numbers in this sequence. Let's have a look at how the pattern is generated. Well, the way it works is that we take some numbers, so we take a 1 and a 1, we add them together and that gives us the next number. Okay? And then we take the 1 and the 2, we add those together to give us the 3. And the way that we generate the next number in the sequence is we add up the 2 numbers before it. So this number here is going to be the previous number plus the number before that. So 13 plus 21 is equal to 34. And we could keep this pattern going. 21 plus 34 equals 55. And we'd see that if we generate the next 7 terms, we'd have 21, 34, 55, 88, 144, 233, and 377. And in fact, this can keep on going forever. We can keep on using this pattern, adding up the 2 previous numbers to find the next one. And this is something that Fibonacci explored during his lifetime. Now, there are lots and lots of patterns that occur in this Fibonacci sequence. And in fact, we can have a look at a slightly different way of generating it. In this, we started with 1, 1. But what if we started with different numbers? Okay, so instead of 1 and then 1 and adding these together to get 2 and then adding 1 and 2 together to get 3, what happens if we start at 2 and 5 or maybe 1 and 3? What I'd like you to do, pause the video now and use the same rule for generating the sequences, but instead start with these different numbers here. So start with 2, 5, start with 1 and 3, and then try starting with 1 and 0, and maybe 1 and -1. And then for a challenge, for those people who feel really confident with this, try using some letters instead. So start with A and B, and of course if you add A and B together, you'd get A plus B. And then what would you get after A plus B when we're adding this and this term together? So pause the video now and see if you can generate some of these sequences. So hopefully you've given that a go now. Let's have a look at some of the solutions to these. So if we started with 2 and 5, then this would be the pattern here. So it would go 2, 5, 7, 12, 19, 31, 50, 81, and 131. So it looks completely different, but it's generated in the same sort of way. 1 and 3, if we started with 1, then 3, we'd get 4, 7, 11, 18, 29, 47, 76. And then these two here are quite interesting. When we start with 1 and 0, well, 1 plus 0 is equal to 1, and then 0 plus 1 is equal to 1 again. And then look at this, we've got 1, 1, 2, 3, 5, 8, 13. This is exactly the same as the original Fibonacci sequence. We've ended up generating this 1 and 1 halfway through the sequence. And similarly, with when we start with 1 and then -1, well, 1 plus -1 is going to give us 0. And then -1 plus 0 is equal to -1, and 0 plus -1 equals -1. And then we have the same sort of sequence again, except everything is negative this time. So quite interesting patterns that are occurring just by changing what two values we start with. And for those of you who gave the challenge question a go, let's have a look. So we have, of course, A and then B, then A plus B. That was just adding together A and B. Then we've got A plus 2B, because that would be the A from here plus B plus another B, so A plus 2B. And then we add A plus 2B to A plus B. Well, that would be 2A plus 3B. Then we'd have 3A plus 5B, 5A plus 8B. And in fact, there's something very interesting here if we just choose to look at the A terms or we just look at the B terms. So if we look at A's, we've got an A here, an A, then 2A, then 3A, then 5A. And then if we just look to the B terms, we've got 1B, 1B, 2B, 3B, 5B, 8B. And in fact, we've ended up having the same sort of pattern as what we had before. 1, 1, 2, 3, 5, 8, 13. And this here is now our first look at using algebra within a sequence. So we're using letters in place of the numbers to generate a more generalized form of this sequence. So moving on, we're going to look at a slightly different sequence now, and we're going to be generating the sequence using 3 lines. So I've drawn 3 straight lines on this page. And what we're interested in is the number of lines. So in this case, we've got 3 lines. The number of crossover points. So that's the times that it crosses over. So here, here, and here. These are the crossover points, which again is 3. And the number of regions. So we've got 1, 2, 3, 4, 5, 6, 7. So we've got 7 total regions. And what we're interested in is what is the maximum number of crossover points and the maximum number of regions. So for this case, when we've got 3 lines, it seems like the maximum is that we've got 3 crossover points and we've got 7 regions. Now, what I want you to do is I'd like you to draw some similar diagrams to find the maximum number of crossover points and regions, but instead of using 3 lines like we've got in this example, I'd like you to try just using 2 lines, and then try using 4 lines and 5 lines. I'd like you to try and draw them and see if you can find the maximum number of crossover points and the maximum number of regions for when we use 2 lines, 4 lines, and 5 lines. And then once you've done that, see if you can predict what could happen if we use 6 or 7 or maybe more lines. Pause the video now, use your pen and paper and have a go at working out these problems. So let's have a look at the solutions here. When we've got 2 lines, it's quite simple. We have only 1 possible crossing, and there are 1, 2, 3, 4 regions. For 4 lines, this is the best possible scenario. We have 1, 2, 3, 4, 5, 6 points where they cross, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 regions. And then for 5, the best possible scenario is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crossing points. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 regions. Now, it can be quite tricky to count those, so you may have to use a ruler to make sure you've got really straight lines and be really careful with counting the regions. But these should be the best possible answers. So I've written out all of the sequences here, and I've also added in this case on the left. This is the case when we've only got one line, and if we only had one line, I'll just draw that now. Well, it's obvious we've got no crossings between lines, and we've just separated it into 2 regions. So that'd be 0 and 2. So now what we have, and I would like you to draw this out as well, is we've sort of generated a table here, if I just do this, of the number of lines at the top, and then we've got the number of crossings and the number of regions. And what we're going to do is we're going to use this to try and figure out what the next terms are going to be. So if we had 6 lines or maybe 7 lines, or perhaps in the future we could look at if there was 20 lines or 100 lines, we want to be able to work that out for any number of lines. We want to work out the number of crossings and the number of regions. So what I've done is I've actually written these out as some sequences. Remember, we're covering sequences today. Well, the number of crossings, the sequence is 0, 1, 3, 6, 10. And the number of regions is 2, 4, 7, 11, 16. Now, this is the tricky part. I'm going to ask you to pause in a moment, and I want you to try and work out what the next 2 or 3 terms could possibly be. See if you can come up with a rule to work out what the terms are. Thinking how to get from one term to the next is a pretty good way of doing that. And then if you can do that, see if it's possible to work out maybe what the 15th term is, or the 20th term. See if you can go way down the line, but without just using the term-to-term rule. See if you can just generate some rule. See if you can come up with some rule for just generating any random term. So pause the video now, see if you can work that out. So hopefully you've given that a go. I'm going to move on now and see if we can come up with a solution, first with the number of crossings. So just looking at the number of crossings, I've written it out like this. I've given it a little bit of space. Now we're going to start by thinking about how to get from term to term. Now this should have been fairly easy to recognise. We see that to get from 0 to 1, well, we're just adding 1. And then from 1 to 3, we're going to add 2. And then add 3 and add 4. And so we recognise that we're just adding on 1 more each time. So the next one would have been add 5, and then add 6, and add 7. And so we can just continue that pattern for as far as we want. But what if we're interested in maybe the 100th term or the 1000th term? If we had 1,000 lines, how many times is the maximum number of times they cross? Well, that's a little bit more tricky to work out, and it would take quite a long time to just keep on adding 1, then 2, then 3, then 4, and keep on going until we get there. So we need to come up with a slightly better way of doing it, and we're going to use algebra to do that. So to do this, we need to think outside the box a little bit, and I'm going to write down 2 times the number of crossings. Okay, so 2 lots of the crossings, in this case, 2 times 0 is 0. Here, we need to multiply by 2, so 2c is equal to 2. Here, 2c is equal to 6, 2c is equal to 12, and 2c is equal to 20. It might seem like I've done that for no reason, it's very random, but actually there's a very good reason for it. It's because we're going to look at the relationship between the number of lines and this new 2 times the number of crossings. So what is the relationship of 1 to 0? Well, that we just multiplied by 0, didn't we? Here, when the number of lines is 2, and we're trying to get to 2 times the number of crossings, which is also 2, well, we've multiplied by 1. Here, 3 to 6, well, we've multiplied by 2. Here, we've multiplied by 3. And here, we've multiplied by 4. Can we see that we're just multiplying by an increasing number this time? Slightly different to before when we said we were just adding an increasing number. This time we're multiplying an increasing number. And the benefit here is that we're staying within one line. we're not having to rely on knowing what there was before. We're just knowing, well, there's 4 lines, we multiply that by 3, and that gets us 12, and then we can divide by 2 to get to the number of crossings. The relationship here is kept within the number of lines. So let's suppose we started at 10 lines. Well, we know that if we multiply 10 by 1 less than the number, so multiplied by 9, and then we took all of that and divided by 2, that should give us the number of crossings. So 10 times 9 is 90, and 90 divided by 2 is 45. So if you had 10 lines, the number of crossings would be 45. In terms of algebra, this relationship can be written as n times n minus 1, all divided by 2. So let's look for a similar method, but this time for the number of regions. Now, this pattern we saw before, we start off by adding 2, then adding 3, and then adding 4. So it's a very similar pattern to what we had before. We're adding an increasing number each time. But this, again, this is relying on knowing what came before. So if we wanted to find the 100th term, so if we had 100 lines, it's going to be quite difficult. We'd have to keep on adding 2, add 3, add 4, and go for quite a long time before we find it. We're going to slightly alter this line. Instead of r equals 2, r equals 4, I'm going to subtract 1 from each of these numbers. So r minus 1 is equal to 1. R minus 1 is equal to 3. R minus 1 is equal to 6. R minus 1 is equal to 10. And r minus 1 is equal to 15. We've got this new sequence now. 1, 3, 6, 10, 15. We've seen that sequence before. 1, 3, 6, 10, 15. That appeared when we were looking at the number of crossings. And what we did next was we multiplied those numbers by 2. So we had 2 lots of r minus 1 is equal to 2. 2 lots of r minus 1 is equal to 6. 2 lots of r minus 1 is equal to 12, and so on. And now we can see that multiplicative relationship between the number of lines and this 2r minus 1 function. So here we have to multiply by 2. Here we're multiplying by 3, multiplying by 4, multiplying by 5, and multiplying by 6. The relationship this time is not the number of lines multiplied by 1 less than that number, but actually it's 1 more than that number. Let's just create a little bit of space at the bottom here, and then I can do some more working. So this time we've got the relationship is n multiplied by n plus 1 is going to be equal to 2 lots of the number of regions subtract 1. Okay, we said if we take this, multiply it by the next number up, it's equal to 2 times r minus 1. Now we can do some algebra on all of this here. We can divide both sides by 2, like this, and that's going to cancel those 2 out. So I'll use my eraser and rub it out. So there we go, there we go. So that means n times n plus 1 divided by 2 is equal to r minus 1, the number of regions minus 1. So now all I need to do is add 1 to both sides. So if I add 1 to this and I add 1 to this, well then this r minus 1 plus 1 is just going to cancel itself out. And finally what we're left with is n times n plus 1 divided by 2 plus 1 is equal to the number of regions. So we're almost at the end of this lesson now, and I'm just going to leave you with one more thing. We're going to look back at that Fibonacci sequence, and I'm just interested in those first 4 terms, so 1, 1, 2, and 3. What we're going to do is we're going to take the first number and the last number, and we're going to multiply them together. So 1 times 3. And then we're also going to look at the middle 2 numbers, so 1 times 2. Work out both of those multiplications, so that's 3 and 2, and then find the difference between those 2 numbers. So in this case, the difference between 3 and 2 is 1. What I want you to do at the end of this video is pick another 4 consecutive numbers. So that's 4 numbers in the Fibonacci sequence that appear next to each other. So it could be 2, 3, 5, 8. It could be 5, 8, 13, 21. And it could be any further down the line. I don't mind. It will get harder the further you go. But you can pick any 4 consecutive numbers. I want you to do the same process. So multiply the first one and the last one together, multiply the 2 in the middle together, and find the difference. So do the larger one, subtract the smaller one, and see what happens. Have a go with some of these numbers in the Fibonacci sequence, and then maybe try some of the other sequences. So the ones that started, 2, 5, 7, 12 maybe. See what happens there. Are there different things that happen for different sequences? And then finally, as one extra challenge, I want you to try this problem of multiplying the first and last and the middle 2 together and finding the difference, but on the sequence that used A, B, A plus B, and A plus 2B. See what happens when you multiply the first and last together, multiply the 2 middle ones together, and find the difference. That's the end of this lesson. I hope you've really enjoyed it, and I will see you next time.